Hey students, this is lesson 822, quadratic patterns. We're going to look at some different patterns and see what quadratic patterns look like. We learned a little bit of that when we were graphing in the last lesson, but we'll do that a little more. Again, I'm going to move to a problem in your homework to give you some concepts that will help us solve the other problems in class. So here's the problem we're going to look at. Imagine several stacks of blocks like the one shown below. So this one has one row. Now rows are going this way. This one has 2 rows. This one has 3 rows, 4 rows, and so on. Complete the table to show the number of blocks in the bottom row as the number increases. So that's just counting the ones in the bottom row. So this first one only has 1. The second one has 1, 2, 3. Third one has 1, 2, 3, 4, 5. Fourth one has 1, 2, 3, 4, 5, 6, 7. And you can see a pattern here. Every time we add a row, it seems like the bottom row is getting 2 bigger. So we keep adding 2. And you should be thinking that this is a linear relationship, which it is. Add a row, add 2 more blocks. So how many blocks would be in the bottom row of a stack with 25 rows? So here we have 10 rows and we have 19. If we kept adding 2 until we got up to 25, that would be one way to do it. So go 19 plus 2 is 21, plus 2 is 23, and so on. But if you notice it's a linear pattern, let's kind of use that idea. Every row we need to add 2. So from here on, to get from row 10 to row 25, I need to add 2 15 times. So I'm just going to do 2 times 15 is 30, and I'll add that on to my 19, and that equals 49. So for 25 rows we have 49. Let's call that row 25 rows. That's equal to 49. Okay. Now with n rows, so we'll say R of n. That's going to be, we know we need to add 2 for every row, so we can take the number of rows times 2. If we do that, though, like if I did 2 times 10, I would actually get 20, which is 1 more than 19. Or if you think about writing equations here, if you go back to the 0 row here, I would need to subtract 2. And 1 minus 2 is -1. So on the nth row, I'm going to have 2n minus 1. All right. Now, if I wanted to know like how many would be on the bottom of the 100th row, I would just do 2 times 100, which is 200 minus 1 is 199. So what is the relationship between the number of rows and the number of blocks in the bottom row? The number of rows is, if I take the number of rows times 2, and subtract 1, I get the number of blocks in that row. All right, now let's talk about something else. What is the total number of blocks T needed for a stack? So notice we were just talking about how many are in the bottom row. Now we're going to talk about adding them all up. So with one row, there's 1 block. So this is the total blocks now. So add that column or that row to your table here. And our total is 1 after that, so we're just counting the blocks. There's 1 there. There's 1, 2, 3, 4 there. 1, 2, 3, 4, 5, 6, 7, 8, 9 there. And, well, my 9 is right here, so I'm just going to take a little shortcut and then add 9, 10, 11, 12, 13, 14, 15, 16. And I'm starting to see a pattern here. It seems to me that if I double this number of rows, not double it, but multiply it by itself, I get my total number of blocks. 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25. Otherwise, the other way you could look at it is you're adding 3, then you're adding 5, then you're adding 7, and plus 9, and so on. So This would be 36 times 6 is 36, 49, 64, 81, 10 times 10 is 100. And notice that the number that we add on is always 2 more than we added on the last time. So what I'm saying here is the difference between the numbers we keep adding is always 2. So it's like the second difference is 2. That is a quadratic when that happens. If you add on or subtract and you change it by exactly the same amount how much you add, that's a quadratic relationship. And we know that this is a quadratic relationship because it's y equals x squared, the number multiplied by itself. So the total number of blocks T needed for a stack with 5 rows is, right here, 5 times 5 is 25. Add a new row to your table for the, oh, we did that already. Write an equation that gives a total number of blocks T. In terms of n, T is equal to n squared. Use this diagram to explain your equation from part F. So what they did is they split it off so that the number of columns is the same as the number of rows, and then flip the extra leftover piece on there, and notice we got a perfect square, and that square is n by n, the number of rows times the number of columns. So we end up making n times n is equal to the total. All right, let's look at one other problem here. And this, so here we're adding up squares again, squares this time. Each square has an area of 1 square unit. Find a formula for the area of the squares A of stage n. Okay, so one thing you might have noticed, at least with these, is if I draw this out like this, I have a perfect square. And I end up with 4 by 4 number of squares in that square, so 4 times 4. But I have to take that 1 off is all, minus 1. So, and this was 3 times 3 minus 1. Because remember we had a blank spot there. 2 times 2 minus 1. And I wonder if that would work. So that's my stage number 2. So in stage 1 I would do 1 times 1 minus 1, which is 0. And notice there's no squares there. So that seems to work. And that's my answer to B. If my formula is area is equal to the stage, oh, they're saying use n for the stage, so n squared minus 1. And if I do 1 squared minus 1, that equals 0, so we would have 0 squares in stage 1. Complete the table. Now you can do it one of 2 ways. I want you to notice this again. Here we add 3, then we add 5, then we add 7. The next thing we would add is 9, that's 24. And the other way you can figure it out is by doing n. So 5 times 5 minus 1, that's 25 minus 1 is 24. 6 times 6 is 36 minus 1 is 35. And notice you would be adding 11 there. When the number that you're adding goes up by a constant, in this case that constant is 2, that's a sign it's a quadratic. And we know it's, the other reason we know it's quadratic is because there's a squared in our formula here. So 7 times 7 minus 1 is 48. 8 times 8 is 64 minus 1 is 63. 9 times 9 is 81 minus 1 is 80. And 10 times 10 is 100 minus 1 is 99, to finish that up. So a couple things you should look for looking for quadratic patterns is an increase that changes by the same amount, or else in the equation you should notice there's a second power. So, and think about this for a second. What if we had this? Does this mean it's quadratic because we're multiplying by 2? And the answer is no, that would be linear. It has to be a power of 2, not multiplied by 2. All right, that's the end of this lesson. I'll see you tomorrow.